look at a different question. So I want to consider, let's say, smooth projective varieties of the same dimension n. So two different smooth projective varieties of dimension n, same dimension n over C. And I want to ask, vaguely speaking, how different are x and y birationally? So how much do x and y differ birationally? So how much do x and y differ birationally? Okay, so that's the vague question we want to consider. Okay, so we want to, the first invariant, which is the kind of the pair invariant, the pair analog of the degree of irrationality, is what we call the correspondence degree. So I'm going to define the correspondence degree between x and y. So what I'm going to do is I'm going to take the minimum over all these correspondences z, and I'm going to be look at the product of, so the minimum over all z of the product of this degree and that degree. So it's the minimum over all z of the degree of the map z over x times the degree of the map z over y. Okay, so I look at all correspondences z. I look at the degree of the map from z to x, the map from z to y. I take the product of their degrees, and that's the correspondence degree. And so this is the natural analog of the degree of irrationality of a variety. So our first proposition is that this satisfies an inequality as follows. So one has that the correspondence degree between two varieties is at most the product of their degrees of irrationality. So the degree of irrationality of x times the degree of irrationality of y. So let's, as an example, say that x and y are very general curves of genera as gx and gy at least one. So let's say that x and y are very general curves of genus, of genera gx and gy at least one. Then I want to claim that we're in this situation of birational independence. So then in fact, the correspondence degree is the product of the gonalities. So it's it's essentially the genus of x divided by 2 times the genus of y divided by 2. And the minimal correspondences are these birational, and the minimal z are, they're birational anyway, 2 fiber products of the gonality maps. So for general curves, you're in this situation where the smallest correspondences arise like this. So you take the gonality map from x to p1, the gonality map from y to p1, and you take z to be essentially the normalization of the fiber product. Okay. So we'd like to, just as in the case of covering gonality, we'd like to sort of say that if you take two very general hypersurfaces, they're, so to speak, is birationally maximum, they're as independent as possible birationally. So here's the theorem. Okay, so let's consider two very general hypersurfaces. So consider xd and ye in Pn plus 1. So these will be very general hypersurfaces of degrees d and e. Very general hypersurfaces of degrees d, e. And again, we want at least 2n plus 2, let's say. Okay. And then the theorem is that the correspondence degree in this case is again the product of the degrees of the irrationality. So it's as big. So then the correspondence degree between x and y is the product of the degrees of irrationality. And remember, that's d minus 1 times e minus 1. And again, minimal correspondences are given by fiber products of projections from a point. And so, and minimal correspondences, again, are birationally equivalent to projections, to the fiber product of projections from points. Birationally equivalent to the fiber product of projections from points. Okay, so how should we define that? So here's the definition. So we'll define the joint covering gonality of X and Y. So we'll just use this covering gonality XY. This is called the joint covering gonality of X and Y. So we're just going to take the minimum over all correspondences Z as before of the covering gonality of Z. And similarly, the covering genus of X and Y will be the minimum over all correspondences Z of the covering genus of Z. So in other words, if we look at this picture, if we have Z here, we're kind of looking, we have X and Y here, we're looking for families of curves parameterized by some variety T so this is a family of curves C sub T, and we look at families of curves that cover Z. So if we have a family of curves covering Z, it gives us a family covering X, and it gives us a family covering Y. So it's a family of curves that simultaneously covers X and Y. That X and Y are very general curves, and maybe genus at least 2 or something of genera, let's say of genera GX, GY, at least 2. Then what's at least true is that the joint covering genus is multiplicative. So the joint covering genus, you can find if you have 2 very general curves of those genera, it's less than 5/4 GX times GY plus some linear term in GX and GY. And it's at least equal to the product of GX times GY plus some linear term in GX and GY. So in any event, if you take 2 very general curves, or very general hyperelliptic curves of genus at least 3, hyperelliptic curves of genus at least 3, then the covering gonality is 4. The joint covering gonality is 4. So the covering gonality is less than or equal to 4 just by the dumb inequality on the upper bound, that the joint covering gonalities is at most the product of the gonalities, but it's equal here. And this uses some of these specialization arguments. So again, they're very weak results that are known, but conjecturally, the picture should be much stronger. So I'll tell you what the proposition is. So let me recall that, well, let me just tell you what the proposition is. So the proposition is that if we take XD and YE, very general hypersurfaces of large degrees, general of degrees greater or equal to 2n plus 2, let's say. So degrees D and E greater or equal to 2n plus 2. Remember that the covering gonality of D and the covering gonality of X is essentially D. Asymptotically, it's D, and the covering genus is asymptotically D squared over 2. And so the statement is that you get added for these joint invariants, you get additive bounds. So the covering gonality of XD and YE is at least D plus E minus something or other, 3n plus 2. And the joint covering genus is XD and YE is at least D squared plus E squared over 2 plus lower order terms.